In just 6 days, it will all be over. On March 16, 2026, 3I, Atlas will glide past Jupiter at a distance of 53 million kilometers, and then it will continue its journey toward Saturn, Uranus, Neptune, and eventually vanish into interstellar space forever. No telescope built by humans will ever glimpse it again. For 8 months, humanity marshaled its greatest scientific arsenal: Hubble, Webb, ALMA, SWIFT, SPHEREX, JUICE, MERCAT, the VLT, Gemini, and Rubin focused on a single 2.6-kilometer object that came from somewhere beyond our solar system. And now, with only 7 days remaining, we are still grappling with questions we cannot definitively answer. Where did it originate? We don't know. Why are its jets separated by exactly 120 degrees? We don't know. In which direction is it actually being pushed? NASA and independent researchers have been openly debating this for 6 days. Will Jupiter's gravity trigger something in it? We don't know yet. And the most profound question, the one that mainstream science hesitates to even ask, was publicly raised by a Harvard astrophysicist back in July. Today, we take a full accounting. Everything we know, everything we don't, and what the March 16th flyby could still teach us before this rare window closes permanently. 7 days remain. Let's start with what we know: the definitive portrait. 8 months of convergent observations have painted a detailed picture of 3I, Atlas. Discovered on July 1, 2025, by the Atlas telescope in Chile, it is the third known interstellar object to pass through our solar system. Its eccentricity, measured at 6.15, is the most hyperbolic ever recorded for a solar system visitor. Its velocity at infinity is 58 kilometers per second, nearly double that of its predecessors. For comparison, Oumuamua entered at 26 kilometers per second, Borisov at 32 kilometers per second, but 3I, Atlas, is blazing through nearly twice as fast. Estimated to be 7 billion years old, it predates our Sun, which itself is 4.6 billion years old, meaning this object has traversed interstellar space for longer than our entire solar system has existed. Its nucleus measures 2.6 kilometers in diameter, a figure refined by Hubble observations in January 2026 after perihelion. It rotates once every 7.1 to 7.2 hours, and its orbital inclination is 5 degrees retrograde, moving almost exactly in the plane of the ecliptic but in the opposite direction of the planets. The chemical composition is extraordinary. Webb and infrared spectroscopy in August 2025 revealed a CO2 water ratio of 7.6, 4.5 sigma above the solar system trend, an occurrence with a 1 in 300,000 probability if it were consistent with typical comet chemistry. ALMA observations between September and October 2025 found methanol at 8% of the total vapor, 4 times higher than the solar average, with a methanol to HCN ratio among the highest ever measured in a comet. SWIFT, observing from July through August 2025, detected water emission at 40 kilograms per second at a distance from the Sun, where such activity is highly anomalous. Webb spectroscopy in December 2025 detected methane in the deep interior, and nickel vapor measurements indicated a nickel-to-iron ratio above solar norms. Morphologically, Hubble revealed 3 mini-jets precisely separated by 120 degrees, using the Larsen-Scheine technique in January 2026, accompanied by a 4th prominent jet pointing toward the Sunday. The anti-tail exhibits a periodic wobble of plus or minus 20 degrees over the 7-1-hour rotation period. Its spin axis is oriented approximately 20 degrees from the sunward direction. Post-perihelion, SPHEREX documented an eruption in December 2025, 2 months after perihelion, with the outgassing shifting from CO2 dominated to a CO mix as surface CO2 was depleted, exposing deeper layers. No technological signatures have been detected. On December 18, 2025, the Green Bank telescope pointed at 3I, Atlas, and recorded no radio emissions above detection thresholds. No signals corresponding to technological transmitters were observed. The object behaves like a comet but defies the norms of anything we've previously seen in our solar system. Yet the scientific drama unfolds in real time, not in the object's ancient history. On February 28, 2026, Federico Spadata, Marata Krakowska, and Luc Donès, published the most comprehensive analysis ever conducted of 3I, Atlas's non-gravitational acceleration, using 7,788 astrometric observations, spanning from May 2025 to February 2026, 10 times more data than NASA, JPL's official solution. They concluded that the transverse acceleration, the sideways push along the orbit, is comparable in magnitude to the radial component, contrary to NASA's claim that it is 5 times smaller. In short, 3I, Atlas is being pushed sideways, not just away from the Sunday. Avi summarized this finding in a March 5 post, emphasizing that official NASA statements can be wrong and science is a learning process. Why does this difference exist? Both teams used rigorous methods. NASA analyzed 782 carefully selected observations using standard quality filters, while Spadata's team used all 7,788 with a different error model, including more post-perihelion data. The A2 component, which represents the sideways push, is highly sensitive to modeling choices, especially during the October 2025 blind window when 3I, Atlas was hidden behind the Sun from ground-based telescopes. The implications are significant. A primarily radial acceleration matches standard cometary outgassing driven by solar heating, but the transverse component requires directional gas emissions that are strongly influenced by jet geometry. And here, the mystery deepens. The geometry is exact. 3 jets separated by 120 degrees, a spin axis 20 degrees from the sunward direction. This configuration naturally favors directional emissions that produce the observed sideways acceleration. The Hubble images and Spadata's measurements converge on a single physical picture, but the symmetry of these jets, the perfect 120-degree separation, remains unexplained. On a normal comet, active jets form irregularly where ice is exposed. They do not distribute themselves geometrically. 3 jets maintained over months with such precise spacing are a geometric regularity that standard physics does not naturally produce. Low, a researcher following this anomaly closely, openly labels it enigmatic, a term scientists use when observations cannot be explained by existing models. Could this symmetry be a technological signature, a form of thruster arrangement? It's possible, but not proven. The arrangement resembles a minimal set of thrusters for stabilizing an object in 3 dimensions. Natural processes can produce something similar, but they do not predict it. The question remains open. 7 days from now, Jupiter's tidal forces may trigger new jets or outbursts. Observing how 3I, Atlas reacts could provide insights into jet geometry and whether the perfect 120-degree symmetry persists or changes under gravitational stress. This is the last chance to test competing models and probe the object's behavior under a new set of conditions. And that brings us to the March 16th flyby, a rare, scientifically crucial event. At 53.6 million kilometers, 3I, Atlas will pass at the very edge of Jupiter's Hill sphere, the zone where the planet's gravity dominates over the Sun's. Small differences in predicted positions between NASA and Spadata's models translate into slightly different encounter geometries, which in turn affect the gravitational deflection and post-flyby trajectory. Precise measurements after the flyby will allow astronomers to determine which model aligns more closely with reality, adding critical constraints to our understanding of its motion. Beyond the flyby's trajectory, Jupiter presents another layer of intrigue: tidal forces. At 53 million kilometers, the gravitational gradient across 3I, Atlas's 2.6-kilometer nucleus, is minuscule. It won't break the object apart, but it may stress zones of ice enough to trigger outbursts. Any sudden ejection of material could reveal the chemistry buried deep within its nucleus, much like the December 2025 eruption observed by Spherex. Methanol, methane, and other organic compounds, previously concealed, might be exposed once more, allowing us a second window into its ancient composition, now interacting with the Sun at a different distance and angle. Meanwhile, ESA's JUICE spacecraft could provide a unique vantage point. During its November 2025 observations, JUICE captured 3I Atlas with 5 instruments while positioned on the far side of the Sunday. The delay in receiving that data just last week means the teams are now processing a different perspective of the object, a side that Earth-based telescopes could not observe. The Janus Navigation and Science camera collected over 120 images, revealing a bright, egg-shaped coma, a halo of gas, and hints of jets and filaments. Once fully analyzed, these images will refine our understanding of the morphology, size, and orientation of the jets before the December eruption. The Magis imaging spectrometer contributed compositional data from 66 million kilometers away. Although its resolution is not comparable to Hubble or ALMA, the unique geometry allowed scientists to detect molecules from angles impossible from Earth. Comparing these measurements with Earth-based observations will refine the spatial distribution of gases in the coma and provide insight into how the unusual chemical composition interacts with solar radiation. The PEP particle detector, on the other hand, characterizes the interaction between 3I, Atlas, and the solar wind, a process shaped by the comet's extraordinary CO2 water ratio, which alters the ionospheric chemistry in ways models have predicted but never directly tested. Taken together, the JUICE data complements Earth-based and other space observations, providing a multi-angle, multi-instrumental view of the object at a critical moment in its trajectory. Yet, the most scientifically significant missed opportunity belongs to NASA's Juno spacecraft. In July 2025, a study by Lowe, Hibbert, and Kra demonstrated that a 2.675 km per second maneuver could have redirected Juno to intercept 3I, Atlas, 2 days before the Jovian flyby, bringing it as close as 27 million kilometers. This wasn't just a passing glance, it could have provided the most detailed measurements ever of an interstellar object. Close-range images of the nucleus, high-resolution spectroscopy of the coma, magnetic field readings, particle detections, and more. The maneuver was technically feasible, yet it was never executed. Reasons likely included budget constraints, the scheduled end of Juno's mission, and uncertainty regarding remaining fuel reserves. The result? Juno remains on its nominal orbit, able to observe only passively and at a far greater distance than it could have achieved. This lost opportunity represents a scientific cost that may never be recoverable. Despite these setbacks, the observations we have gathered over 8 months are revolutionary. The combined data across dozens of telescopes and instruments have fundamentally changed our understanding of interstellar objects. First, 3I. Atlas demonstrates that prebiotic chemistry can survive intact over billions of years in interstellar space. Methanol, HCN, and methane found in its deep interior prove that these building blocks of life, formed in a protostellar disk 7 billion years ago, can endure cosmic radiation, extreme cold, and isolation, only to be released and chemically active when exposed to solar heat. This is no longer theoretical, it is directly observed. Second, the chemical diversity of other planetary systems is now measurable. The elevated CO2 water ratio, extreme methanol enrichment, and unusual nickel isotopes indicate a protostellar environment colder and older than our own. The universe does not produce identical comets, and this diversity can now be quantified, not merely inferred. Third, interstellar objects of this size are not rare. Population estimates suggest that at any given time, at least one object like 3I, Atlas may be present in the inner solar system. This implies that Earth, during its formation, may have been routinely bombarded by interstellar bodies carrying foreign chemistry, seeding the solar system with prebiotic material from beyond. The implications for planetary formation and astrobiology are profound, shifting our understanding from theoretical models to measured reality. As we approach March 16th, the tension in the scientific community is palpable. The object will pass just at the edge of Jupiter's Hill sphere, and the predictions of NASA and SPADA differ subtly but meaningfully. These differences translate into slightly different gravitational deflections, altering post-flyby trajectories in ways that can now be measured. Even small deviations could confirm or challenge our current models, providing a critical test of the physics governing interstellar object dynamics. Yet even with all these measurements, some questions remain unanswerable. The 1-2-0 degree jet symmetry, the exact origin of the object, and the nature of its sideways acceleration are anomalies at the edge of conventional cometary physics. Lowe's assessment places 3I, Atlas at a 6 out of 10 on his scale, where 0 is definitively natural and 10 is definitively technological. This does not suggest artificial origin, but quantifies the uncertainty. Several features are improbable or unexplained within standard frameworks. The Hill sphere coincidence with Jupiter has a probability of 1 in 26,000. The CO2 water ratio is 4.5 sigma above expectations. Methanol enrichment is 4 times normal, and the non-gravitational acceleration remains disputed. No radio signals were detected, ruling out active technological emission, but a passive object cannot be excluded. Every anomaly individually has a plausible natural explanation, yet the statistical probability of all occurring simultaneously challenges conventional expectations. It is a puzzle that refuses closure. Even after the flyby, some questions will remain open, waiting for future missions or serendipitous observations to refine our understanding. And yet, the March 16th encounter offers the final window to witness this object within the solar system. Saturn awaits in July 2026, Uranus in April 2027, Neptune in 2028, and then 3I, Atlas will continue forever into interstellar space, beyond our reach, silent and unyielding. The data we gather in these coming days will be the closest we ever come to this ancient traveler, a 7-billion-year-old relic formed in a distant protostellar disk, carrying chemical clues from a solar system not our own. The stakes could not be higher. Every telescope, every instrument, every observation counts. The teams are working in real time, integrating JOICE data with post-flyby astrometry, refining models, and preparing for the moment when predictions meet reality. This is the edge of scientific opportunity, a convergence of decades of instrumentation and human expertise, culminating in a fleeting encounter that will never recur. As March 16th approaches, every observation, every calculation, every telescope trained on 3I, Atlas becomes part of a final, unrepeatable experiment. Jupiter will pull at it with precise gravitational force, just at the edge of its Hill sphere, and scientists will watch for the subtle deflections that may finally reveal which orbital model NASA's, or SPADA's, more accurately describes this object's behavior. Even a few kilometers of difference in predicted position could tell us whether the sideways acceleration is purely natural, driven by the unique jet geometry, or something more unusual. Observing its response to Jupiter's tidal forces might also trigger new outbursts, exposing interior layers and revealing chemistry previously hidden from view. These eruptions could offer unprecedented insight into the deep composition of an interstellar traveler, now fleetingly within our reach. The anticipation is palpable because the 120-degree jet symmetry remains unexplained. This feature alone is an enigma. In a natural comet, active jets form irregularly where ice is exposed at fractures, craters, or erosion zones. They do not organize themselves into perfectly spaced geometric patterns. Yet, 3I. Atlas maintains this symmetry across months of observation, suggesting a physical configuration so precise that it aligns with what a minimal thruster system might require for three-dimensional stabilization. It's not proof of technology, but it is a geometric and dynamical coincidence that challenges our understanding. If Jupiter's gravity provokes changes in this configuration, we may finally have clues to decipher the forces shaping these jets, whether they are purely natural or influenced by mechanisms we have yet to fully comprehend. Meanwhile, the combined dataset from Earth-based telescopes, space observatories, and JUICE is forming an integrated picture of an object that is both familiar and alien. Methanol, methane, and HCN, preserved over 7 billion years, demonstrate that prebiotic chemistry can survive interstellar journeys intact, providing strong observational support for the idea that life's chemical precursors travel between stars. The unusual CO2 water ratio, nickel enrichment, and other isotopic anomalies show that not all planetary systems produce the same chemical outcomes. Interstellar comets are not copies of our solar system's comets, they are evidence of stellar diversity, now measured rather than inferred. Population estimates suggest that objects like 3I, Atlas, are not rare, implying that interstellar visitors may have influenced the chemical evolution of the early solar system. Earth's formative years could have included repeated bombardments by such objects, delivering prebiotic compounds from distant stars. This observation transforms speculation into a grounded understanding. Interstellar chemistry is real, measurable, and potentially consequential for the origins of life. Yet, even with these profound insights, 3I Atlas keeps its secrets. The exact origin remains unknown. The precise mechanics behind its perfect jet symmetry defy conventional physics. Which model truly predicts its path, and how Jupiter will influence it, remains unresolved until we have post-flyby data. Every anomaly pushes the boundary of our knowledge. The Hill sphere coincidence with Jupiter is a 1 in 26,000 chance. The CO2 to water ratio is 4.5 sigma beyond normal expectations. Methanol enrichment is 4 times the typical amount, and the transverse acceleration is debated between 2 rigorous teams. No radio signals have been detected, eliminating active technological sources, but not a passive object. Lowe's scoring system quantifies the uncertainty at 6 out of 10, neither conclusively natural nor technological, but firmly in the domain of anomalies that resist closure. In just 7 days, we will witness whether Jupiter's influence triggers new activity, offering a live test of these puzzles. The post-flyby astrometric data, combined with the JUICE November observations, will allow scientists to integrate months of previous measurements into the first truly comprehensive model of an interstellar object in motion through our solar system. For 9 months, dozens of instruments, hundreds of researchers, and thousands of observations have converged on this single object, and now the final act unfolds. After Jupiter, 3I Atlas will continue towards Saturn in July 2026, Uranus in April 2027, Neptune in 2028, and then out into interstellar space, never to slow down, never to transmit a signal, and never to answer the remaining questions. This flyby is the last window to witness, measure, and test theories against reality. Every observation counts. Every instrument contributes to a dataset that will never be repeated for this object. What we know is extraordinary. A 7-billion-year-old object, formed in a protostellar disk colder and richer in carbon than ours, carrying record concentrations of prebiotic molecules, with 3 jets at exactly 120 degrees, and exhibiting lateral acceleration that 2 highly credible teams measure differently. What we don't know is equally profound. Where it originated, why the jets maintain perfect symmetry, which orbital model is correct, how Jupiter's gravity will influence it, what the JUICE data will reveal, and ultimately, the question that remains technically open, what this object truly is. This is the kind of moment that defines the limits of human observation. 8 months of effort, dozens of instruments, hundreds of researchers, thousands of papers read, submitted, revised, and debated, all culminating in a single, fleeting flyby. After March 16th, the window closes. 3I Atlas will continue on a silent trajectory into the void, leaving behind data but no object. We will have answers to some questions, and new mysteries will emerge from what we observe. So, here's what you can do. Subscribe to follow the flyby results in real time. Share this with someone who has been following 3I Atlas from the beginning. And tell us in the comments what you hope Jupiter reveals. In 7 days, we will know what 3I Atlas can teach us, and then it will be gone, never to return. The universe has handed us this rare opportunity, our chance to witness an object older than the sun, a relic from another star system, carrying the chemical seeds of life itself. Every second, every measurement counts. Don't miss it.